So again, we're talking about Maclaurin and Taylor series. We're just going into example problems. As you can see here, here's the table of the important Maclaurin series that we've discussed. We haven't necessarily derived all of them. I think we did talk about, we definitely talked about the geometric series, the first one here. We derive e to the x. Sine of x and cosine of x. It's basically derived using, the easiest way to derive it is using the general formulation, the nth derivative evaluated at a over n factorial x minus a to the n equals 0 to infinity. This is basically brute force way of coming up with the Taylor and Maclaurin series. Of course, for Maclaurin series, a is centered at 0. And that's how you would find sine and cosine. Tangent x I'll be talking about towards the end of discussion. Ln of x is basically integrating the geometric series with x being negative x. So you replace x with negative x and basically integrate both sides to come up with tangent inverse. Because remember, the derivative of arctangent x equals 1 over 1 plus x squared. Also, I misspoke. We're replacing x with negative x squared. Then we're taking the antiderivative to come up with arctangent x. Okay, and then this last one is the binomial series, which was kind of that funky one that I talked about last time. We have this binomial coefficients. Remember, it was k. It was read k choose n, which is given by this kind of pattern that you can see the coefficients here. And if you have more questions on that, I can answer any questions that you guys might have after discussion as well. So let's jump into the first question is arctangent of x squared. So this is f of x. And we haven't derived arctangent x yet. So this is where we're going to start with arctangent x and get the definition for arctangent x squared. So as I've suggested here, we're going to start with this form. So we're going to start with our geometric series, 1 over 1 minus x. This equals 1 plus x squared plus x cubed plus dot dot dot. And this, of course, equals the sum x to the n equals 0 to infinity, right? And the radius for this is 1. And this comes, you can either use ratio test or it comes directly from the definition of geometric series where absolute value of r has to be less than 1. So now we're going to modify this a bit and try to get it in the form of arctangent, the derivative of arctangent, which is 1 minus x squared, right? So now this right-hand side, we're replacing x with minus x squared. This is minus x squared plus x to the 4th. This should be minus x to the 6th plus dot, dot, dot. And now, and of course, if you wanted to change this notation too, you can do minus x squared to the n equals 0 to infinity. R will stay the same. Because absolute value of r is negative x squared, which is less than 1. So absolute value of x is still less than 1. Your radius of convergence doesn't change there. Now we take the antiderivative of both sides, because this guy is the same thing as 1 over 1 plus x squared, which is a derivative of our arctangent x. So this is arctangent x prime. So if we take the derivative or antiderivative of that, we'll be left with arctangent x, which is 1 over 1 plus x squared with respect to x, and we can integrate this this series term by term. So if we do that, we'll be left with x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 dot dot dot, so on and so forth. And we can integrate this guy as well. Sometimes it's easier to just identify the pattern and write it out explicitly from what you wrote out here. We'll do both. So let's try writing it out just from reading this. So we're starting with x, and it increments by odd numbers, right? So we'll have x to the 2n. Now you can either do +1 or -1 here, right? So the 2 will always make it even, and then we can either subtract 1 or add 1. It really doesn't matter. So I'll choose to add 1. And then also our denominator also increments as odd numbers, right? 1, 3, 5, 7. So we'll keep that same pattern, 2n plus 1. And then as you can see, the signs alternate. So we'll have a -1 to the n. So at first, I just index it at n, but I always go back and check if that needs to be modified to work with the series that I have here. So for it to work with this 2n plus 1, n would have to start at 0, right? So if n starts at 0, it would be x to the 1 power over 1. And then we'll just check this -1. Yes, it'll be -1 to the 0, which is just +1. If we plug in n equals 1, we have 2n, which is 2 plus 1. So x cubed over 3, and then -1. So that's our second term. So it looks like it's going to work out. So that's good there. So this is just by identifying the pattern that we have in our series. We can also integrate that guy. So, oops, can't spell integrate. Integrate. If we do that, it'll be integral -x squared to the n equals 0 to infinity. Okay, so now we can move this integrand inside of the summation. That helps you visualize, right? And I'm gonna distribute this n power. So there's really a coefficient of -1 in front of this x squared, right? So it'll be -1 to the n times x squared to the n will be simplified to x to the 2n dx, right? We're integrating with respect to x. Now, this -1 to the n, since we're integrating with respect to x, is just a constant, okay? Because this n is only incremented by this sum operator, right? So it's basically a constant inside of the integral. So n equals 0 to infinity -1 to the n, and then we'll integrate that. It'll be 2n plus 1 over 2n plus 1, right? It's +1 power over that power. And of course, with any integral, indefinite integral, we need a constant of integration. So don't forget your plus c. Now, in order to solve for the c, we plug in a value of x. We judiciously choose our value of x such that we can isolate our c. So looking at this expression, more often than not, you're going to choose x equals 0, but that may not be the case all the time. So if we chose x equals 0, if x equals 0, c would equal, the right-hand side would be 0. Arctan of 0 is 0. So c would also equal 0, right? Actually, when I integrated this, I should have a plus c here. I forgot to add, but there should be a plus c there as well, right? And actually here as well. So c is 0 when we solve for that. And so this expression here, I know it's getting a little messy, matches this expression that we found here, right? So we verified that for both methods. Either way, we can find the same notation as a summation. And also, we knew the radius of convergence before we integrated. And as I've mentioned before, when you integrate or differentiate a series, it will not change the radius of convergence, and our radius of convergence will still stay 1. But of course, if you didn't remember that, you can always, it's always safe to just go ahead and apply the ratio test or the root test to find the radius of convergence. And I actually strongly recommend that you just get in the habit of doing it. That way you don't miss easy points. That way you don't have to memorize any rules. Any questions so far on this one? Okay, so actually we didn't finish the problem. We just derived arctangent of x. But once we have that, finding arctangent of x squared is as easy as just plugging in x squared for x. So arctangent of x squared is going to be x squared minus x squared cubed, which is x to the 6 over 3, plus x to the 10th over 5, minus dot, dot, dot. And this, we just replace x with x squared here as well. So x squared to the 2n plus 1 becomes x to the 4n plus 2 over 2n plus 1, and 1 to the n equals 0 to infinity. We already found that this was 0, right? Where, okay, so now let's go to the second problem. The second problem is x equals x cosine of 2x. Okay, so we start with our known series cosine of x, right? R is infinity, and we'll replace x with 2x, right? And then multiply it by x over here to get our desired series. So we'll start with cosine of x, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus, right? This is equal to, it alternates, so negative 1 to the n even powers of x over 2n factorial. This starts from n equals 0 to infinity, r infinity. If you didn't know that, again, ratio test, you can find that r is infinity. Now we're going to add, we're going to replace x with 2x, so cosine of 2x. So I'm doing this step by step, just so you can see all the intermediate steps that we do to get to the final answer. So now we're just replacing everything with all the x's with 2x. All right, so we can do that to the sum here. 1 to the n, 2x to n over 2n factorial. right? And finally, we can multiply the expression above by x. So we'll have x minus x times 2x squared factorial x times 2x to the fourth over 4 factorial 2x to the 6 over 6 factorial, and so on and so forth. And I can do that to the sum as well. So we'll have negative 1 to the n times x times 2x to the 2n over 2n factorial. And I can simplify this a bit by combining, I'm going to combine the x term with this x term here, but first I need to separate out this 2 to the 2n. So negative 1 to the n to the 2n, and then I can combine this x, which is x to the 2n plus 1, right? Divided by 2n. Right, and of course, find the radius of convergence. Limit as n approaches infinity of an plus 1. So 2 to the 2n plus 2, x to the 2n plus 2n plus 2 plus 1 is 2n plus 3 over 2n plus 2 factorial. So that's my an plus 1 divided by an. So I'm going to multiply by the reciprocal. Okay, so that's 2n factorial. 2 to the 2n, x to the 2n plus 1. Of course, I'm dropping the absolute value, or the negative 1 to the n because of the absolute value. So let's cancel this out with this 2n, this, with this. That'll leave me x squared, right? This 2n factorial, I can cancel out with that, and I'll be left with 2n plus 1 and 2n plus 2, okay? So because it's a factorial, that n plus 1 term generated 2 additional terms instead of 1. So now, so this is ratio test, right? We're doing. This is L, which is equal to that. So now we're left with the limit of x squared over 2n plus 1, 2n plus 2. This is 0, which is always less than 1. The radius is still infinity. Okay. All right, so now let's look at the next one. Of x equals x squared ln of 1 plus x cubed. So same technique as before. Nothing changes now, except instead of starting with cosine, we're going to start with ln of 1 plus x, right? Because we have that written as a series, and we can replace x with x cubed and then multiply that series with x squared. So again, ln of x was derived from the geometric series. We know that the derivative of ln of 1 plus x, so ln of 1 plus x prime, is going to be 1 over 1 plus x. So it would make sense that we can start with the geometric series 1 minus x and integrate that, right? So we start with the geometric series 1 minus x, replace x with minus x, then integrate in order to get ln of 1 plus x. So that's kind of the strategy. If you didn't have this memorized, or if you weren't given this series, you can always start with the geometric series and be able to derive it. So we'll start with ln 1 plus x, which is given as x minus x squared over 2, x cubed over 3, x to the 4th over 4, the sum. It's written as -1 to the n minus 1, x to the n over n. And this starts from n equals 0 to infinity. And the radius for this is 1. Yes, radius is 1. So now, we'll start from the inside. Ln of 1 plus x cubed. So I'm replacing x with x cubed. So I'll have x cubed minus x to the 6th power 2 plus x to the 9th over 3, x to the 12th over 4. The sum is -1 and -1. I mean, you don't have to write this in between. I'm just writing it for practice so you guys can see. X to the 3n over n equals 0 to infinity. Right, so now x squared 1 plus x cubed. So now I'm multiplying by x squared for every term. So x to the 5th, x to the 8th, x to the 11th, x to the 13th. Right, and then we'll multiply an x squared in here. So with combining it with this base, we'll have x to the 3n plus 2 over n equals 0 to infinity. Right, so now, will this change my r? No, but we can check it. So limit an plus 1 is x to the 3n plus 3 plus 2. There's 3n plus 5 over n plus 1 times n over x to the 3n plus 2. This cancels out with this 3n and 2 of these, so we'll be left with x cubed. And if we take the limit of this guy here, we're left with 1. So our limit is equal to x cubed less than 1. So take the cube root, so x is still less than 1, r is still equal to 1, right? Any questions on anything so far? So far, so good? Ooh, sorry, I neglected the chat for a second. Shouldn't the sum start from 1 to infinity? Which one are you talking about? This ln? Are you referring to the ln thing? Is it? Oh, yeah, you're right. It is 1. Sorry. Yeah, this should be 1. Sorry, I had the chat open and then it hit itself. Restructure this. There we go. So it's your preference if you want to write everything out step by step. I do it that way, so I'm less likely to make mistakes. Once you get comfortable with it, if you don't want to write every step, you should be able to skip the intermediary step and maybe do a couple steps in one. So if you feel comfortable, yeah, feel free to, you could probably jump from this to this. I think it's just easier to go step by step, and that way you don't make any mistakes. Okay, so moving on. So I think we've seen plenty of examples on those types of problems. We can also use Taylor and Maclaurin series to evaluate limits. So using the definitions that we have and sort of almost basically treating series as like variables and plugging it into algebraic expressions and simplifying everything algebraically and applying limits. So we'll use series to evaluate limits. So the first problem, limit as, it's supposed to be x approaches 0 of x minus ln of 1 plus x over x squared. Right, so now we have to evaluate a limit. And we can recognize that we have this known series here. So we can use the series ln of 1 plus x as a base, and then algebraically manipulate this expression so that we can kind of simplify everything. So if you look above, ln of x is given here, right? R equals 1. So we'll start with that. We'll start with negative ln of x instead of writing it out twice. So negative ln of x, negative will be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot, dot, dot. And this equals the sum n equals 0 to n equals 1. Keep doing that. Right? Equals 1, yeah. N equals 1 to infinity of x. This is alternating, so negative 1 to the n minus 1, x to the n over n. Okay, yep. So now from there we can add x, right? So if we add x, I'll just write it on the same line. I'm going to add x. So we'll add x here. And now notice we can evaluate, we can distribute this negative sign inside here, and this x will cancel out with this x. So we'll have positive x squared over 2 plus minus x cubed over 3 plus x to the 4th over 4 plus dot, 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 or minus dot, dot, dot. And this equals, since we took out this guy here, this was minus, right? So when I added x here, I should add it to this side as well. But now this x is gone, and I extracted the first term out of this sum here, right? I extracted the first term out of there and canceled it out with this x. And we should still have a negative because all these signs are flipped. But since we extracted the first term out, we should start our indexing from n equals 2, right? So that's what we're left with here. We'll have negative 1 to the n minus 1, x to the n over n, right? Now, honestly, we could have skipped this step altogether. I'm just showing you that you can simplify it that way in case maybe that was the end of the problem. But what we're trying to get to is this final step where we're dividing it by x squared. I guess you shouldn't skip it because as you're simplifying, as I'm putting more steps into it, you're going to have to do it here anyway. So you might as well just go do all these intermediary steps to keep tabs of it. Otherwise, it could get confusing at the end. Okay, so now I'm dividing each term by x squared. So I have 1/2 minus, actually I'm going to leave some space up front, 1/2 minus x over 3 plus x squared over 4 minus dot, dot, dot. This right hand will be divided by x squared. So that's the same thing as multiplying by x to the minus 2. So x minus 2, right? At the end. And now this is equal to this expression here. And now I just have to take the limit as x approaches 0. So let's take the limit as x approaches 0 of this whole thing. And if x approaches 0, all these terms drop out. They all turn to 0. Except this first term here. So this is, the limit is equal to 1/2, right? So if I want to be consistent, I should have a limit here. This would be equal to 1/2. Okay, so this is our final answer there. So I really didn't have to do everything over here on the right. I'm just showing you all the ways that you can write this expression, because again, sometimes it might be easier to deal with the written out form, this, or sometimes it's easier to deal with your sum notation. So just, I would get in the habit of practicing to do both. You should be comfortable with writing it in either way. Any questions on that? Okay, I have a couple more problems. They're very similar. Okay, so next one is limit as x approaches 0, sine x minus x plus 1/6 x cubed x to the 5th. So basically almost same, pretty much the same steps as above. I mean, it's the same idea. We start with a known series. So from this expression, we know sine of x, right? We know sine of x. We have it up here. We can express it as a Maclaurin polynomial right here. So we start with that. Sine of x, some space here, sine of x. That's equal to x minus x cubed over 3 plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, dot, dot, dot. Right? And now I want to subtract x and add 1/6 x cubed. Okay, so I'll just do both of those at once. So this goes on forever. So I'm going to subtract x plus 1/6 x cubed. Right, this x can cancel out with this x. And even though we can't see it right away the way it's written, this is actually equivalent to this, but this guy's negative, right? So 3 factorial, this is the same thing as x cubed over 3 times 2 times 1, which is x cubed over 6. So this is negative. So we can cancel out this guy with this guy. Now we're left with x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 dot. Right? And now we need to divide by x to the 5th. X to the 5th, so we'll divide by x to the 5th here. And we'll be left with 1 over 5 factorial minus x squared over 7 factorial. The next one would have been plus, it was 9th, so x to the 4th over 9 factorial minus so on and so forth, right? And now this guy here is equivalent to this expression. So now we just have to evaluate the limit. So limit as x approaches 0, sine x minus x plus 1/6 over x cubed over x to the 5th. So I'm going to squeeze this limit term in here, right? And except all the terms except the first one go to 0. The first one's the only term without an x in it, so this will be 1 over 5 factorial, which is equal to 1 over 120. So now, one thing I forgot to mention on both of these problems. So this is how you would solve it if you were to use the definition of the series and simplify algebraically. But unless the problem was, unless in the problem it asks explicitly to do it that way, another way you can look at it is to use L'Hopital's rule when possible. So if we look at this first problem here, remember when you take the limit of something, and let's say an, and this equals 0 over 0 or infinity over infinity, you can apply L'Hopital's rule. And look at this case here. We have x, so that'd be 0 minus ln of 1 is 0 over x squared is 0. So that is a 0 over 0 case. We could have used L'Hopital's rule. Right, so this is method 2. We use L'Hopital's rule with the derivative of the top and the bottom. So the derivative of the top would be 1 minus 1 over 1 plus x over 2x. So now if we apply the limit, it is 1 minus 1. So that's 0 over 0. So we have to use L'Hopital's rule again. We can use L'Hopital's rule again. So we'll have 0 minus, actually this would be 1 over 1 plus x squared now. The negative will cancel out, and then the denominator will be 2, right? So now if we apply the limit here, we have 1/2. And this matches our answer that we got using the definition of the series. So unless the problem specifically tells you to do it, I'm sure if the point on if the exam question was trying to test you this, he would probably ask you explicitly to use the definition to simplify it this way. But if you wanted to double check, you can see how simple it is to apply L'Hopital's rule and come up with the same answer. And the same thing can be done with this second problem here. If you apply the limit, evaluate the limit at x equals 0, sine of 0 is 0, minus 0 plus 0 over 0 to the 5th is 0. So let's try L'Hopital's rule. So this would be cosine x minus 1 plus 3/6 is 1/2 x squared over 5 x to the 4th. Evaluate at 0. Cosine of 0 is 1, minus 1 is 0, plus 1/2 times x squared is 0 over 0. So we have to use L'Hopital's rule again. L'Hopital's rule. Derivative of cosine is negative sine minus 0 plus 1x. So x. This will be 20x cubed. So evaluate the limit. Looks like it's going to be 0 over 0 again. Sine of x is 0 plus 0 over 20. 0 cubed is 0. Let's apply it a third time. So you can do this as many times as you get 0 over 0 or infinity over infinity. So this would be negative cosine x plus 1, 60x squared. Cosine of x is minus cosine of x is minus 1. So 0 over 0 again. Let's keep doing this until get something else. Derivative of cosine will be sine now. Back to sine over 120 x. Still 0 over 0. All right, I promise this will eventually end. So last time it looks like we'll have cosine of x 120. So now we have 1 over 120, which matches our answer here. Okay, it's probably the same amount of work as this one over here when we use the definition of a series, but again, you have multiple ways of doing it unless the problem explicitly tells you to use the definition of a series. All right, so last problem. This is, where's the problem? All right, so this one asks for the limit as x approaches 0, tan x minus x over x cubed. So this is the last problem, 3. Okay, so now we're not given the definition of tangent in this table. We have arctangent, we have sine and cosine, but no tangent. But we do have sine and cosine, and we know that the definition of tangent is sine x over cosine x, right? So we're going to do that. We're going to use that relationship for tangent. So we're going to start with tangent here. Tangent x equals sine x over cosine x. Sine x is defined to be, I have a cheat sheet here, so I'm looking off that as well. X minus x cubed over 3 factorial, x to the 5th over 5 factorial minus dot dot dot. That's sine. Cosine is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. So what do we do from here? We need to do long division. So I know this can be very painful, but if you needed to, at least you know how to do it. So we have x cubed factorial, and then dot, 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 dot. And then we'll write a few terms out here. I'll just do the first couple just to give you an idea of what we need to do. So this 1 goes into this x times, right? 1 times x, x squared minus x squared over 2 factorial times x would be minus x cubed over 2 factorial plus x to the 5th over 4 factorial, right? So x times x 4th over 4th. Now, minus sign in front of this whole thing. Okay, and now I subtract. So I get 0 here. This second column I'll have minus x cubed over 3 factorial plus x cubed over 2 factorial. So let's write this on the side. X cubed over 3 factorial plus x cubed over 2 factorial. So it looks like I need common denominator. So this one, if I multiply a 3 here, that becomes 3 factorial, right? So that means I need to do it to the numerator. So I'll just rewrite this denominator as 3 factorial. You can rewrite it as 6 if you feel more comfortable doing that. So 3x cubed minus 1x cubed, this will give me 2x cubed over 3 factorial. So 2x cubed over 3 factorial. And then now the sum of negative x to the 5th over 5 minus x to the 5th over 4. So same thing, I'll write it off to the side. Easier to see. So minus x to the 5th 4. So this should be, I should multiply this top and bottom with 5. So then the denominator here becomes 5 factorial. So what am I left with? I think I'm missing a sign here. This should have been plus. So this should be plus. Okay, sorry, this should have been a plus here. So I should be subtracting this from a positive x to the 5th over 5 factorial. And this should leave me with negative 4 x to the 5th over 5 factorial, right? So you see negative 4 x to the 5th over factorial. And now I see how many times this 1 can go into this term, right? This term here. And that would be plus 2x cubed over 3 factorial, right? So I basically repeat this process now. So I multiply through 2x cubed over 3 factorial, and then I multiply these two. Again, this is very painful, I know, but this is basically how the book derives it. So this would be minus 2x to the 5th over 2 factorial times 3 factorial. There's a lot of algebra here, I know. So now you get the idea, though. That's how you do it. So actually, if you wrote out the rest of these terms, I'm not going to go through all these steps. You would get 16 x to the 5th over 5 factorial, dot, dot, dot. And actually, this simplifies to x plus x cubed over 3, right? The second term, the denominator here, 3 factorial is 6, so 2 over 6 is 1 over 3. So, and then 16 over 5 factorial, believe it or not, is 2 over 15. So 15 plus dot, 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 right? So we could rewrite tangent this way. So now this is tangent x as a series. This guy here. And the radius of convergence, of course, you can write this as a sum and do ratio tests to find the radius of convergence. But there is a theorem that says if you multiply or divide two series together, right, two convergent series together, and both of their radii are the same, then your product or quotient will also have the same radius of convergence. So since the r for sine is infinity and the r for cosine is infinity, the r for tangent is also infinity. Okay, so I'll just quickly finish up. Well, actually, we'll just wrap it up here because now it's the same process as before. We know the series here. We subtract x, divide by x cubed, and we can evaluate the limit there just as we did before. So I can continue with this problem on Wednesday, and I'll finish it up for you guys. And I'll give you guys an update on how we're going to move forward for Friday and if we need to do a midterm review as if we were taking the midterm or not. So if you have any questions, feel free to stay after. I'll stay on for a little bit. So otherwise, thank you for joining me.